Today we will be talking about an interpretation of the Laplace transform using linear algebra concepts. We will then talk about the energy interpretation of mechanical system behavior, alluding to the fact that as energy goes down, system behavior also quiets down. Although the latter concept may look somewhat abstract at the beginning, it will turn out to be exceedingly useful in your future studies of any dynamical system, controlled or uncontrolled. So, first, let us talk about the Laplace interpretation, the eigenvalue interpretation of the Laplace transform. So, what I need to do is remind you about a few facts for linear algebra. Linear algebra is mostly concerned about finite dimensional vectors. We will be seeing what the equivalent of that is for functions. Second, in linear algebra, we have objects such as vectors, like x in Rn, and we have that the vector is made of n entries, x1 ranging through xn. Now, with these vectors, we also have matrices. And to make things simple, we'll have matrices such as matrices A, and I will consider only square matrices. That is, A belong to n, r to the power n times n. Okay? And the matrix A has its own set of entries, A11 through A1n. That's for the first row. For the first column, it's A11 through AN1. And then we complete the last row and the last column by adding A and N at the end. And often we are interested in things such as A times X. And when we compute A times X, we know that it takes roughly n squared operations. Okay, and that's a huge pain. And sometimes we want to reduce that. Okay. Not only that, but we also are interested in obtaining simplified expressions for the effect of A on X. And so for that, we have invented concepts such as diagonalization. Doesn't work all the time, but nevertheless, we have that. And what does it mean? It means that we find certain vectors x, okay, which call maybe x sub lambda, that satisfy the following property. X sub lambda is not 0, and a times x sub lambda is equal to lambda times x sub lambda, where lambda is real or complex. And we are interested in finding these x lambdas and the corresponding lambda for the purpose of simplifying our computations. How does it work? Well, really, it works as follows. Suppose you know all the eigenvalues and the eigenvectors x lambda and lambda. Suffice this. First of all, we must remember that in case A is diagonalizable, then we have only, let's say, n such x of lambda, okay? There are n eigenvectors, okay, corresponding to the number of eigenvalues, lambda 1 through lambda n. So what I'm going to do is I'm going to call the corresponding eigenvectors, which I will, for the sake of convenience, call x1 through xn. Watch out, because this is not the same x1 through xn as the components of x that I have expressed in the previous view. So that we have a times x sub I is equal to lambda I x sub I. Now, we know that if we do our job right, these x1 through xn can be written as, can be a basis of Rn in such a way that any vector y I can write as let's find some notation here. Maybe mu1 times x1 plus mu2 times x2 plus etc. plus mu n times xn. Okay, and that's by definition of x1 through xn being a basis of Rn. So let's say we want to compute a times y. Well, so there's the old-fashioned way, which is we compute a11 times y1, the component, or let me write y here component-wise as y1 through yn. We can compute it as the vector a11 times y1 plus a12 times y2 plus etc. plus a 1n times yn. And same thing for the second row all the way to the last row, an1 y1 plus an2 y2 plus etc. plus ann times yn. And we realize that this corresponds to 1, 2, 3, 4, 5. Okay, so it's going to be n squared multiplies and also n squared adds. Okay, so let's look at some consideration with eigenvectors. So y and eigenvectors. Y, as I said, has entries or canonical entries y1 through yn. And what it means is that y is equal to y1 times e1 plus y2 times e2 plus etc 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 plus yn times en, where e1 is the vector made of 1 on top and then zeros everywhere else. E2 is made of the vector 0, 1, 0, and then 0 everywhere else, etc., etc., etc. Okay, if I call that basis C for canonical, then I can just add a C here to say that these are the entries of Y in that basis. Now, with the eigenvectors x1 through xn, I can also write that Y is equal to a certain mu1 times x1 plus a certain mu2 times x2 plus etc 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 plus a certain mu(n) times xn. Okay, and that is the reason for that is that x1 through xn is, from linear algebra results, a basis of Rn, just like e1 through e2 through en is a basis of Rn. However, because this one is different, we call it B. And so, in that basis, we write that the vector y is, in shorthand, mu1 through mu(n). Okay, and that is in the basis B. Now let's look at computing A times Y. So computing A times Y in the basis C implies n squared multiplies and n squared adds. Okay, now let's compute AY but in the eigenvector world, well, we know that AY, because AY will be something like this. Okay, I take y and I multiply it by a. Okay, would be mu1 times ax1, but ax1 is lambda1 x1, okay? Plus mu2 times ax2, which is mu2 times lambda 2 x2, all the way to mu n times lambda n xn, where lambda 1 through lambda n are the eigenvalues of A. As a result, the entries of A times y in the basis B are simply mu1 times lambda 1, mu2 times lambda 2, all the way down to mu n times lambda n. Now, what you can see is that these constitute only n multipliers. What does that mean? That means that if you're going to use A very often, you better use the basis x1 through xn to do your computations, then the original basis e1, e2 through en. Okay? Because the original basis requires you, when you compute A times y, to do n square multiplies and n square adds, whereas in the new basis, you have only n multiplies. Okay? And if you do it very often, then you're going to have to do like a number of n multiplies. And the only thing that costs is the original diagonalization. Okay? So it's the original diagonalization, okay, that costs. And that usually costs somewhere between n squared and n cubed operations, depending how you do it. Okay? But if this is just an upfront cost, okay, then the only cost that matters is the recurrent cost, which is as many times the number of times you have to compute A times y, as opposed to the original diagonalization of A, which is expensive but happens only once. So, such is the value that traditional eigenvalues reach. Now, we would like to understand whether there is anything similar to that happening with the use of dynamical systems. So, for that purpose, what I'm going to do is first clear this picture. And then ask, what is the story for dynamical systems? So for that, I first want to remind you that at the beginning of this lecture, we considered vectors x with component 1 through n. Okay, x1 through xn. Okay. Now, what is the equivalent for functions? So a function of time. Okay. What is it? Well, traditionally, we represent it as follows. We represent it as the function, versus time. And it may look like this. Okay. Now, suppose that instead I was trying to store f as a vector. Okay. Then we could imagine that f as a vector is the following: f of t1, f of t2, f of t3, f of t4, etc., etc., etc. Of course, you can imagine there is an infinity of entries for f. However, we could say that those entries are precisely the components of f, just like x1 through xn are the component of x. Okay. Now, that being said, that is the only difference between the representation of a finite dimensional vector and a function f, which is definitely an infinite dimensional vector. Whereas this one is finite dimensional. Okay? Alright. So, and just like for a finite vector, we write it in short as xi, I between 0 and n, we have that we can write a shorthand f of t, where t is between 0 and infinity. Okay? Now, like matrices that act on x, we have things like operators, okay, which I'm going to write A like this, that operate on f, a function f. So, what could it be? Well, instead of a matrix, for example, an operator A that applies on f could be something like this. The derivative of f. Okay? The derivative of f is an operator, and in fact it is a linear operator. Okay? Which means that d dt of f plus lambda g, two functions, one number, is equal to d dt of f plus lambda d dt of g. And just like ax is a vector with x being a vector, d dt of f is a function when f was also a function. Therefore, operators take functions, return functions. Just like matrices take vectors, finite dimensional vectors, and return vectors. Where does this take us? Well, I'm going to show you a few other interesting operators. Okay? One of them is integral. Integral of f. So, for example, integral from 0 to infinity of f is also a linear operator. Why? Because integral from 0 to infinity of f plus lambda g is indeed equal to integral from 0 to infinity of f plus lambda integral from 0 to infinity of g. Okay? So linear operators are like linear functions or their representation by matrices. Now, if you remember, what we're going to do now is apply all this to dynamical systems. Okay, so for dynamical systems, we're going to show that it is also an operator. Okay, so for that, let me clean up everything. And take a linear system. Okay, so for linear dynamical systems, we have seen two important concepts. One of them was the transfer function, h of s. The second is the impulse response. And of course, remember, we also have seen the differential equation. If we assume zero initial conditions, it is equivalent to know the transfer function, the differential equation, or the impulse response. Okay, where the impulse response is h of t. Okay, so this thing, and that thing are equivalent. So we also remember that the following happens. Okay, if I have an input function which we call f, okay, then the output, which is the response of the system, is in the frequency domain or in the Laplace domain will be something like output of s. So let me not forget the hats, okay? We'll probably have to add a hat here. Is equal to h hat of s times f of s. Okay? In the time domain, the output of s, sorry, there is no hat, the output of t will be H star F of t. Okay? So, what is H star F? This H star F is the convolution operator. Now, let's compare how much it costs to compute this with how much it costs to compute that. Okay? Here, a convolution is integral from 0 to infinity of h of tau f of t minus tau d tau. Okay? Without much of thinking, you can see that this guy costs a lot more than computing this guy, provided you have h of s and f of s. Let's say compact values of h of s and h of s. Okay? So for a given value of t, then it's more expensive to compute h star f of t than for a given s to compute h of s times f of s, which is just one multiply. Okay? Here, you can think about the number of multiplies and the number of adds by looking at, for example, the way you would discretize this expression. Okay? And you will end up with a lot more multiplies and adds than here. So, another way of saying it is that in the Laplace domain, okay, it is much easier to deal with the effect that dynamical systems have on inputs than in a time domain. Now, let's push the comparison a little further by thinking, isn't the Laplace domain just another way of representing f? It's like a change of basis. Okay? Isn't Laplace like a change of basis? For infinite dimensional vectors. If it is, then we can draw a direct parallel with the fact that for finite dimensional systems and vectors, there are bases such as the eigenvector basis, for which it is much easier to compute the effect of a given matrix A on vectors than the original canonical basis. Here, that would be what happens in the original canonical basis, and that would be what happens in the new basis. To summarize, in the finite dimensional case, we have that the original job was to compute A times X, and we concluded that it was costly when A is arbitrary. However, we can find in a new basis that the same quantity can be computed as A tilde times X tilde, where X tilde is the new expression of the coordinates of X. A tilde is the new expression for A, where A tilde is now not arbitrary at all, but is made of the diagonal matrix containing the eigenvectors, the eigenvalues 0, 0. Okay? And this is cheaper to compute. Typically, computing A times X costs on the order of n squared operations. This one costs on the order of n operations. Now, the equivalent in the Laplace domain is that in a time domain, so let me say Laplace here. In the time domain, we need to compute output of t is equal to the integral from 0 to infinity of h of t times I, the input of t minus tau, d tau. Oh, let me correct a few things here. This one and this one. Going back, this is h of tau, the impulse response of the system, times I, the input of t minus tau, d tau. Okay? And this is costly, especially if we need to compute that at all times t, all t's. Now, O of s is equal to h of s times I of s with the proper hats everywhere is easier and cheaper to compute. In both cases, instead of having a bunch of multiplies and adds, which you see here and you see there, because we multiply h with I and then we sort of sum from 0 to infinity, so it's like a product followed by the sum. Here we have just n products there, and then we can add them up or whatever. Here we have the same way, just one product per instant of S. Okay? And so this is the extent to which these two quantities, on the one hand, the business of eigenvalues, eigenvectors computation, on the other hand, the business of Laplace transforms, are related. The extent to which we can push this connection further is still unknown to me, and I will therefore abstain to going any further.